Big M Simplex method. Let us see the introduction. When the constraints in linear programming problem are less than equal to types, as for example 2x1 plus 3x2 less than equal to 17, simplex method is used. But when the constraints in the problem are greater than or equal to types, as for example 5x1 plus 6x2 greater than or equal to 25 or 12x1 plus 20x2 equal to 100, to solve such problem many methods are available. One of them is the Big M method. This method is also known as penalty method. Let us see the steps involved in Big M method. Number 1. Check whether the objective function of the given LPP is to be maximized or minimized. If it is to be minimized, then convert it into a problem of maximization using the relation maximum z equal to minus times minimum of minus z. As for example, minimum z equal to 24x1 plus 28x2, then we can write it as minus maximum of z equal to minus 24x1 minus 28x2. Number 2. Check whether all bi's are non-negative. If any of the bi is negative, then multiply the corresponding constraints by minus 1 so as to get all bi's non-negative. As for example, x1 minus 3x2 plus 5x3 less than equal to minus 7. Then we convert the above constraints into, by multiplying minus 1 on both the sides, we get minus x1 plus 3x2 minus 5x3 greater than or equal to 7. Step 3. Convert all inequality of the constraints into equality by introducing slack and or surplus variable in the constraints. Put the cost coefficient of these variables equal to 0 in the objective function. In case of introducing surplus variables, to get the initial basic feasible solution, we need to introduce artificial variable, and the cost coefficient of two variables in the objective function is minus m, where m is very large positive number. As for example, number 1, 5x1 plus 4x2 less than equal to 2000, which implies 5x1 plus 4x2 plus s1 equal to 2000. Here s1 is slack variable. Second, x1 plus x2 greater than or equal to 300. Then we write x1 plus x2 minus s2 plus a1 equal to 300. Here s2 is surplus variable and a1 is artificial variable. In the objective function, we put 0 coefficient for s1 and s2 and minus m for a1. Number 3. If the objective function is maximize z equal to 3x1 plus 7x2, then with respect to the above constraints, we can write it as maximum z equal to 3x1 plus 7x2 plus 0s1 plus 0s2 minus m into a1. 4. If the objective function is minimize z equal to 3x1 plus 7x2, then we convert it as a maximum z equal to minus 3x1 minus 7x2 plus 0s1 plus 0s2 minus m into a1. Step 4. Prepare initial or first table of simplex method as shown below. Now we prepare the table shown here. In the first line, we write the values of the cost coefficient C1, C2, Cj, Cn. Then in second row, we write Cb, Yb, Xb, Y1, Y2, Yj, Yn, S1, S2 and A1. And then we fill up all the rows and columns according to the given restrictions. Note, in column Yb, we write S1, S2 up to A1 such that the columns S1, S2 up to A1 make identity matrix. Step 5. In the above table, we compute Zj minus Cj, which is equal to Cb into Yj minus Cj. That is, Zj minus Cj for column Y1 equal to 0 into A11 plus 0 into A12 up to plus 0 into AM1 minus C1, and Zj for column Xb equal to 0 into B1 plus 0 into B2 plus 0 into Bm and so on. Step 6. A. If all Zj minus Cj greater than or equal to 0, then the initial basic feasible solution in the column xb is an optimum solution. B. If at least one zj minus cj negative, then proceed on the next step 7. Step 7. If there are more than one negative values of zj minus cj, then choose the most negative of them. Suppose it be zr minus cr for some j equal to r. Then check A. If all yi are less than equal to 0, that means all the values in the column yi are less than equal to 0, then this is an unbounded solution to the given problem. B. If at least one yi are greater than or equal to 0, then corresponding vector yr enter into the basis yb. Step 8. Compute the ratio xbi upon yir for all yr greater than 0 and choose the minimum of them. Let the minimum of this ratio occurs for kth row, that is xbk upon ykr is minimum. Then vector yk will leave the basis and in column yb write yr in place of kth value of yb. Here element ykr, that means element of kth row and rth column in the first table, is called pivotal number, and kth row is called pivotal row and rth column is called pivotal column. Step 9. Then we compute other entries of the columns of xb, y1, y2, yj up to so on in the second simplex table using the following formulas. A. New pivotal row equal to old pivotal row divided by pivotal number. B. Other new row equal to old row minus pivotal column coefficient multiplied by new pivotal row. Step 10. Go to step 5 and replace the above procedure until either the optimal solution is achieved or there is an indication of unbounded solution. The decision regarding the optimum feasible solution is taken as follows. All zj minus cj greater than or equal to 0 and there is at least one artificial variable in the basis with non-zero value, then LPP has no feasible solution. But if artificial variable is present in the basis with 0 value, then the solution is considered as optimal. 2. If all yi are less than equal to 0 in column yr, for which zr minus cr is most negative, then there is an unbounded solution to the problem. Let us consider the following problem to understand the Big M method. Example 1. Here we have given the problem for minimizing, that means minimize z equal to 4x1 plus x2 subject to the constraints 3x1 plus x2 equal to 3, 4x1 plus 3x2 greater than or equal to 6, x1 plus 2x2 less than equal to 3 and x1 and x2 greater than or equal to 0. Let us see how to apply Big M method. So, first of all, we convert the constraints into equations by using necessary slack, surplus and artificial variables. Let us see first constraint 3x1 plus x2 equal to 3. Here we need to add artificial variables, but no use of slack or surplus variables, and we write it as 3x1 plus x2 plus a1 equal to 3. From the second constraints, we write 4x1 plus 3x2 minus s1 plus a2 equal to 6, and from third constraints, we write x1 plus 2x2 plus s2 equal to 3. Now we convert our objective function from minimization to maximization as minus maximum z equal to minimum of minus z, which is equal to minus 4x1 minus x2, and adding slack and surplus variables with 0 cost coefficient and artificial variable with minus m cost coefficient, we write the objective function as minus maximum z equal to minus 4x1 minus x2 plus 0 s1 plus 0 s2 minus m into a1 minus m into a2. Now we prepare the first simplex table as follows. In this table, the first row indicate the values of Cj. In second row, we prepare different columns heading Cb, Yb, Xb, Y1, Y2, S1, S2, A1, A2, and in last column we compute the ratio. In table 1, we arrange the coefficient of third constraints in the first row, the coefficient of first constraint in second row and coefficient of second constraint in third row. Then we calculate the values of Zj and Zj minus Cj for the column of xb and then after for all the columns respectively. Then in last column we calculate the ratio xbi upon yir. Here the most negative value of Zj minus Cj is for the column y1, so it is called pivotal column, and minimum ratio for the second row having numerical values, so it is called the pivotal row, and the cross element of the pivotal column and pivotal row is called pivotal number, which is 3 denoted by red color. Let us see table 2. In table 2 similarly we keep all the headings as it is and we calculate the cell values using the formula. Now new pivotal row or new second row equal to old pivotal row, that means old second row, divided by pivotal number. Here pivotal number is 3, so we divide by 3 to the old pivotal row having elements 3, 3, 1, 0, 0, 1, 0. By simplification, we get new pivotal row with elements 1, 1, 1 by 3, 0, 0, 1 by 3 and 0. And new first row equal to old first row minus pivotal column coefficient into new pivotal row. Substituting the values of old first row, which are 3, 1, 2, 0, 1, 0, 0. Corresponding pivotal column coefficient is -1 and new pivotal row is 1, 1, 1 by 3, 0, 0, 1 by 3, 0. On simplifying, we get the elements 2, 0, 5 by 3, 0, 1, 1 by 3 and 0. Similarly, we calculate second new row using the formula, the elements old row 6, 4, 3, -1, 0, 0, 1, corresponding column coefficient multiplied by -1, so we get -4, and new pivotal row 1, 1, 1 by 3, 0, 0, 1 by 3, 0. On simplifying, we get the element of second new row 2, 0, 5 by 3, -1, 0, -4 by 3 and 1. Substituting these values in the table, we compute Zj minus Cj. Here Zj minus Cj is the most negative for y2 column and minimum ratio for the first row as well as third row. We choose randomly one row and one of them let us consider third row as pivotal row. That is, A2 will leave the basis and y2 will enter the basis, and we prepare table 3 by calculating new pivotal row and new other rows in similar way. This is the table 3 in which we have calculated all the values of the different rows and columns. Here the new first row we have calculated using the formula old first row minus pivotal column coefficient multiplied by new pivotal row. Substituting the elements of the old first row, which are 2, 0, 5 by 3, 0, 1, -1 by 3 and 0, corresponding pivotal column coefficient 5 by 3 multiplying minus sign, and elements of new pivotal row 6 by 5, 0, 1, -3 by 5, 0, -4 by 5 and 3 by 5. On simplification, we get the elements for the new first row as 0, 0, 0, 1, 1, 1, -1. Similarly, we calculate second new row. Substituting the elements of the second old row, multiplying the column coefficient 1 by 3 with minus sign and carrying the elements of the new pivotal row. On simplification, we get the elements of the second new row as 3 by 5, 1, 0, 1 by 5, 0, 7 by 9 and -1 by 5. Substituting these values, we prepare table 4 as shown in the table. The values are entered and calculated the values of Zj minus Cj. Here the second new row is calculated again as usual formula, and we get the elements of the second new row as 3 by 5, 1, 0, 0, -1 by 5, 26 by 45 and 0. Similarly, third new row is calculated with the usual formula, and the elements of the third new row become 6 by 5, 0, 1, 0, minus 3 by 5, minus 7 by 5 and 0. Here all Zj minus Cj greater than or equal to 0. So, we reached at optimal solution and no artificial variable present in the basis with non-zero level. Therefore, the optimum feasible solution is x1 equal to 3 by 5, x2 equal to 6 by 5 and minimum value of z is minus times minus 18 by 5, that means 18 by 5. Now, we consider another example in which the problem has no feasible solution. Let us see example 2. Here example is for maximizing the given value z. So, maximize z equal to 3x1 plus 2x2 subject to the constraints 2x1 plus x2 less than equal to 2, 3x1 plus 4x2 greater than or equal to 12 and x1 and x2 greater than or equal to 0. Here first of all we convert the constraints into equations using the necessary slack, surplus and artificial variables. First, in constraints 2x1 plus x2 less than equal to 2, we need to add slack variable and we write it as 2x1 plus x2 plus s1 equal to 2. Second, for the second constraint 3x1 plus 4x2 greater than or equal to 12, we should subtract surplus variable s2 and add artificial variable a1. Hence, it becomes 3x1 plus 4x2 minus s2 plus a1 equal to 12. Now, we set our objective function as maximize z equal to 3x1 plus 2x2 plus 0s1 plus 0s2 minus m into a1. Hence, we can prepare first simplex table as shown here. Here first row is again the value of the cost coefficient in the objective function. Second row indicate the labels CB, YB, XB, Y1, Y2, S1, S2, A1 and in the last column we calculate ratio. Substituting the coefficients from the constraints we can get first table and now we calculate values of Zj minus Cj. Here column of Y2 has most negative value of Zj minus Cj which is minus 4m minus 2. So, this column is called pivotal column. The minimum value of the ratio which is 2 in the last column is for the first row. So, the first row is called pivotal row. The intersection value of the pivotal column and pivotal row is called pivotal number which is 1. Table 2. Here we substitute the computation of CB, YB, XB, Y1, Y2, S1, S2 and A1 columns and again recalculate Zj minus Cj. Here first we compute new pivotal row using the formula new pivotal row which is here in our case new first row which is equal to old pivotal row or old first row divided by pivotal number which is equal to 1 divided by 1 into the elements 2, 2, 1, 1, 0, 0. That means again simplification remains as it is, the elements remains 2, 2, 1, 1, 0, 0. And now we calculate new second row using the formula old second row minus pivotal column coefficient multiplied by new pivotal row. The elements of old second row are 12, 3, 4, 0, minus 1 and 1. Corresponding pivotal column coefficient is 4 and multiplied by minus sign. Consider the new pivotal row with elements 2, 2, 1, 1, 0, 0. On simplification, we get the elements 4, minus 5, 0, minus 4, minus 1 and 1. Here all Zj minus Cj greater than or equal to 0 and artificial variable a1 is in the basis with values 4 which is non-zero and therefore, LPP has no feasible solution. Let us summarize the talk. Simplex method is used only when the constraints are less than or equal to type, but when the constraints are greater than or equal to or exactly equal to types, then big M method is used. For such types of constraints, we should use surplus and artificial variables. In objective function, the cost coefficient for surplus variable is taken as 0, but for artificial variable the cost coefficient is considered as very large number, say capital M with negative sign. Thank you.